Hello, everybody. Welcome to the USB Brown Bag, US edition. Tonight, June 18th, 2014. I'm your host tonight, John Harris, and tonight we're going to be covering the CCNA DC Data Center cert, and this will be part one of two. We've got Tom Hollingsworth on the line. He can be reached on Twitter at Networking Nerd. We're going to go ahead and got a couple of housekeeping items before we hand it over to Tom. The first thing is, obviously we've got these all over the world now. We're global, so if you're just kind of watching a recording or anything of that sort, definitely, if you're not within the U.S., check out one of the others in one of the other regions. Other thing to keep in mind is, as we're going along, you can follow the Twitter or the vBrownbag hashtag there. That's also where you can post questions. You can also post them in the questions section there on GoToMeeting, and we'll get those filed up to Tom here. Another thing to keep in mind is we just kind of want to keep people aware that if you still have any CCNA routing and switching questions, we still got a contest going on there. You can tweet your questions to Scott, and that's that Scott M at 32768 on the vBrownbag hashtag, and that'll basically put you in a contest to enter to win the Networking for vSphere Admins or CCNA Cert Guide, and that's going to be going on through June 30th, 2014. Scott's running that contest, so definitely hit him up on Twitter and give him some good questions, because I'm sure he'd love to answer those for you. And with that being said, I'm going to go ahead and give me a moment here. I'm going to switch it over here to Tom and let Tom kind of proceed here. And like I said, if you guys have any questions along the way, definitely just kind of put them up on the Twitter hashtag or through the questions window. And with that being said, I'm going to go ahead and hand it off to you, Tom. How you doing this evening?
I'm doing pretty good. Thanks for having me on.
Oh, totally.
Hello to everybody out there listening and watching along. My name is Tom Hollingsworth. For those of you who may not know who I am a CCIE. Got my CCIE about 3 years ago, but I have been a CCNA since 2005, back before there was a data center CCIE. It was just the plain old CCNA. I'm also a networking speaker and a networking blogger. You can find my blog over at networkingnerd.net. And when the guys at vBrownbag asked me to come on and do a talk about the CCNA Data Center, I said sure, because it's one of the hot certifications out there right now. It's great that we're starting to see Cisco focusing away from routing and switching only and into other technologies that are becoming more crucial to people. And data center is definitely going to be one of those technologies that you're going to want to take a look at. So let's look at the CCNA Data Center real quick. If you go to www.cisco.com/go/certification, it will bring you up to the training and certification page. And if you scroll down through here, you'll see that there is a CCNA Data Center link under the certification tracks, under Associate. When you click on it, it will bring up a list of the exams and recommended training for those exams. CCNA Data Center is a two-part exam. The first part, 640-911, is the Data Center Networking exam. This is more of the traditional thing that you would think of coming from Cisco. It's a lot of questions about networking theory and things like VLANs and Cisco networking features. 640-916, DCICT, Introducing Data Center Technologies. This is where a lot of the other technologies come into play from the data center realm. So if you scroll down through here and click on details, it will tell you all of the things that you need to learn on here. For instance, Fabric Path is going to be on the test, on the DCICT test, or storage networking. There's a lot on here about initiator targets and SAN connectivity. In fact, I'd almost bet you're going to have some fiber channel questions on here. The important thing to remember is that the two halves kind of stand on their own. One is about networking. One is about the other things. There's a lot of product knowledge on these exams, so you need to know the difference between the different Nexus switches, the different types of Cisco UCS servers, and so on and so forth. And remember that it is an introductory level exam, so they're not going to be crushing your soul with 3 or 4 hours of practical questions where you have to wire things together. So, make sure that you study hard, that you understand the material and the applications of the material. And as we'll go into a little bit here in just a minute, applications of the material are absolutely key, because Cisco is notorious for not asking you very straightforward questions. They want you to kind of think outside the box.
Hey, Tom.
Yes.
I've already got a question here in the question window. So Graham Mitchell had a question, and his question is the routing and switching a good prerequisite for this data center exam, or would that be of any value to take prior to getting into the data center piece?
Yes. I would say that the Route Switch CCNA has a very good crossover, especially with the DC-ICN exam. The fundamentals of networking are the same, no matter whether you are in a data center or you are in a campus LAN, which is what routing and switching is kind of focused on. The only difference is the routing and switching CCNA only tests you over vanilla iOS, Cisco's Internet Network Operating System. So you're going to be running it on workgroup switches. The iOS that's tested on the CCNA Data Center is Cisco's NXOS, the operating system that runs their Nexus switching line. While they're similar, they're just different enough to be have some little translation problems. And I'm actually going to cover NXOS a little more in depth next week, because this week I wanted to concentrate on some of the networking fundamentals that you would find in both CCNA Route Switch and CCNA Data Center. And I know that Scott probably has covered a lot of these in the last couple of weeks, but I wanted to hit some highlights so that people kind of understood how the carryover between data center networking and campus networking is accomplished, because there are a lot of similarities there.
Great. Thanks for that.
All right, so let's just jump right in here. I know you guys are going to love lots of slides. By the way, for those of you who have never attended one of my presentations, I am kind of a pop culture nerd, so some of the slide titles may make you chuckle, and feel free to get a good laugh out of it if you recognize some of my humor. Every networking exam in the world is going to start with a concept called the OSI model. This is the generic model that we use to show how networking data flows up and down the stack of a network card or of a system or something like that. So if you see here, there are 7 layers, and you will have to memorize them. I actually had to memorize this model in college when I thought I was going to be a database administrator, and I walked out of the test and said, I'm never going to need to know this again. And now it's tattooed on the inside of my eyelids, and I can never forget it. The most important layers are going to be down here, starting at layer 1, 2, 3, and 4. If you are a networking technician, you can pretty much draw a line here above transport and forget about these top 3 layers, because you will never really deal with them. You deal a little bit in the session layer, but it's not necessarily important. But layers 1 through 4 are where you are going to live, because this is where all of the networking hardware behaves. From cabling at physical layer to IP addresses at the network layer, things like that. So make sure you understand the concepts of these 4 models, these 4 layers of the model. We're actually going to go into those a little bit in depth. But the most important thing that I can tell you about the OSI model is that, just remember, it's not a hard and fast rule. It's a conceptual idea to help us get our head around the way that these things behave. So with that, let's go on to the actual layers of the model. So layer 1 is the layer closest to the hardware. This is the physical layer where all of the electronic communications occur. And I'm going to talk to you a little bit through each of the layers about the work unit. So when you talk about the physical layer, bits are what's actually being transferred in this layer. When a lot of people just generically refer to whatever it is as a packet. But for the purposes of the exam, you need to know the actual work unit that happens. So when you're talking about the physical layer, bits are what's transferred. That's where everything in the above layers gets put into an electrical signal and then thrown onto a cable somewhere. cabling in a data center, you see a lot of category 5, 5E, and 6 copper wires. You also see a lot of fiber. Fiber is really popular because it doesn't have electrical attenuation, and it also is higher speed. You know, with server interfaces, 1 gig, now 10 gig data center backbones, or 40 gig going to 100 gig. The tolerances on copper are not good enough to get that high speed. In fact, the tolerances on fiber is kind of difficult as well. So what you're seeing is a lot of multiplexing of large fiber strands into smaller, into units to achieve those speeds, like things like quad fiber connections to get to 40 gig. But with physical, the thing you have to remember is this is the connectivity layer. This is the one that everybody always forgets about. Is it plugged in? Not just power, but with networking as well. And one of the things that Cisco likes to talk about to kind of illustrate these layers is the network devices that live at them. Layer 1 is the most basic of these layers. The most basic layer 1 device is a repeater. And this is simply a device that takes an input signal and it regurgitates it. It reconditions it and sends it out the other end. Think of it like an extension cord for your network. It just makes the segment a little longer. These were important back in the day when you were using the old Ethernet that ran on thick coax cable, because you had some very strict distance limitations. We still do with copper cables, but it's not as strict as it used to be. And so you needed a repeater to get the signal further down the segment on a bus, and we'll cover buses in just a little bit. But repeaters are not very smart. They're actually some of the dumbest things around, because all they do is they hear an input signal and they regurgitate it as an output signal. And it's one input and one output, and that's it. So you don't really see a lot of repeaters anymore, and if you do, I really apologize, because those things can be taken out in the street and hammered until they break. But one thing you probably have seen at Layer 1 is a hub, and you'll see up here in the corner, this is the Cisco marketing icon for a hub. You should know the Cisco marketing icons for the basic devices that you're going to see, because Cisco uses them everywhere, and a lot of other manufacturers use Cisco's as well. The hub is a multi-port repeater. That's all it is. It gets an input here, and it electrically copies that information and sprays it out all of the ports that are connected to it. Think of it like a power strip, not a surge protector, but just a plain power strip. It gets power input and provides that power input to every other device on the connection. Now, hubs are great because they provide multi-port connectivity, but hubs are bad because they don't have any intelligence. They're just stupid pieces of electrical hardware. And we used hubs for a very long time in networking because we didn't really have any other options. Today, finding hubs in your network is usually a panic moment. I can remember doing some network engineering for some of my schools, and I would actually go track down hubs in the walls and rip them out, because someone would go down to, say, like Best Buy and buy a cheap little $20 hub so that they could hook up 2 or 3 computers in the classroom. But it causes huge networking concerns, because since it's an unmanaged device connecting multiple hosts, we can't have any control over what those hosts are doing. So a lot of the Layer 1 devices that you're going to run into on the CCNA Data Center exam are there for historical purposes only, so that you kind of understand what they're about.
Hey there, Tom. Got a couple other questions that came in. One of them is, what voltage do the cables run at?
If the cable is carrying a power signal, it's usually 48 volts DC. Now, you typically don't see a lot of that unless you're using a power over Ethernet switch, because there's not a lot of, most of the electrical signals that are being carried are being generated by the end device and shot down the line. It's actually one of the reasons why we have cable limitations. It's because of the attenuation in the cable pairs. The data just kind of starts leaking out after a while. So I wouldn't worry so much about the voltage on the cables as I would unless you're using some kind of powered device.
Gotcha. I think that they were just kind of curious. Those type of questions are probably going to come out. Another one somebody asked was, and this may have been better for a little bit later, but we'll go ahead and get it out there. Does Cisco have any labs that would be, a good place for them to go and get some experience while they're getting ready for the exam?
Yes, actually there are a couple of different labs that you can use. Cisco does have some labs available at their Learning at Cisco site.
Okay.
We'll cover that a little bit. But one of the products that's coming out, and it's not out yet, I really wish it was, is Cisco Modeling Labs. You may have heard it referred to as VIRL, V-I-R-L. It's a product that Cisco is putting out that it virtualizes iOS and allows you to build topologies and configure things on them. It's a real popular tool, not just for people that are learning, but for people who want to model their existing network to do things like changes. So what's going to happen if I add this particular protocol to that switch? Is it going to cause me problems? The reason I hesitate to bring up CML and VIRL right now is, one, because they're not shipping, and two, NXOS is not going to be available on VIRL the day it ships. They're having some issues getting the NXOS image available for that. But one nice thing about VIRL is it's going to be completely free to end users.
Wow, that sounds awesome. Just
Yeah.
from many standpoints, whether you're trying to troubleshoot, check things out, or just learn, that's pretty cool.
Yeah, they kind of have to do that because there have been some technologies that have been released over the course of the last, I don't know, maybe 5 years that have really helped with people doing virtualized iOS deployments. One you might have heard of if you're in the networking world is Dynamips. It also goes by a couple other names, Dynagen, GNS3. Those are kind of wrapper programs. Those allow you to emulate a specific iOS image on a desktop. There are two problems with that, though. One, it's not entirely legal from Cisco's standpoint, which is one of the reasons why I don't recommend people using it now that we have another option available. And two, it will chew up your processor horribly. When I was doing my CCNA labs, I would use GNS3 and Dynamips to simulate certain lab functions, and once I got to about 4 routers, my laptop was hot enough to cook eggs on, and my fan never stopped running.
Wow,
Yeah.
that's interesting. So keep that in mind, guys. You might want to avoid those resources, or they're resource hogs.
Yeah, I highly recommend using CML VIRL and Cisco's other options. One of the options you can use for NXOS if you have a VMware host running around is something called the Nexus 1000V. It's a completely virtual version of NXOS that runs kind of like a soft switch, almost like a VMware distributed switch.
Yep.
And I'll cover that a little bit more next week when we get into NXOS.
All right. Well, thanks, Tom.
No problem. So we're done with Layer 1 because Layer 1 is pretty simple. It's electrical signals only. Layer 2 is where the fun starts happening. So on the OSI model, Layer 2 is your data link layer. This is where all of your host-to-host communication happens. The work unit at Layer 2 is a frame. I know a lot of people that talk about Layer 2 packets, and they're all wrong. Frames are what happens at Layer 2. Every networking machine in the world has an address that is used to communicate at Layer 2. That's a media access control, or MAC address. This is a 48-bit number that is burned into the networking card of every device ever created. Every iPhone has a MAC address, every laptop has a MAC address, every switch has a MAC address. This is how hosts communicate with each other electronically. We talk about IP addresses a lot when we talk about host-to-host communications, but as you get into the nuts and bolts of the way that networks work, that IP address actually has to be converted into a MAC address for those two machines to talk on the same network. One thing you'll need to know for the exam is the difference in the MAC address. So typically when you see a MAC address, it's listed as 6 groups of numbers, and they're both 2 numbers each. So you may see like 01:FF:64. Those are all in hexadecimal, by the way. 256 character combinations per field. The first 3 fields are the OUI. That's the manufacturer-specific unit identifier. With the first 3 numbers of a network card, you can tell what device or what manufacturer made that device. And you can actually look up the OUI online. The last 3 numbers are network card specific. And every time Cisco makes a new phone or they make a new router, that network card is going to have a unique MAC address, because if it doesn't, if you have 2 devices on the same network with the same MAC address, they're both going to receive the traffic for whatever you're sending. It actually causes a bunch of problems. And it has to do with the way that Ethernet is designed. So Ethernet is a broadcast protocol. When you send a packet on an Ethernet network, every host on that layer 2 network receives a copy of that packet. Now, the ones that it's not destined for, they just ignore it. But the ones who are supposed to get it will wake up, listen, and respond. And so that's why you have to have unique MAC addresses everywhere. So we're talking about what happens when you have a device at layer 1. Layer 1 devices, remember I said they're not very intelligent. Well, one of the problems that we have with Ethernet, since it's a broadcast medium, is that we can't have so many devices talking all at once. Ethernet actually has a built-in methodology for detecting when devices are chattering over the top of each other. Carrier sense multi-access collision detection, CSMA/CD. You may hear this brought up a lot, especially when someone starts talking about Ethernet. And the way that it works is when you have a device on the network and it starts talking and somebody talks over the top of it, both of those stations on the wire detect that the packets ran into each other. And every device knows that a collision occurs. So what happens when that occurs is that every host connected to that segment has to stop talking for a certain period of time. There's a back-off timer built into the network protocol stack. And then it looks to see if it can talk again. Because of that, the more hosts you have populating a segment, the more likely that there's going to be a collision. And so that's why we have artificial sizes for the amount, or artificial numbers for the amount of hosts that you can locate on a particular segment. And that particular area is called a collision domain. So the more hosts you have in a collision domain, the more likely you are to start having collisions, which means that every host has to stop talking until the CSMA/CD backoff timer is elapsed. So we want to try to shrink the collision domains as much as possible. And we definitely don't want to try to tie more than one together. That was the original problem that we solved at layer 2 with a device called a bridge. And here's a lovely gratuitous shot of the Golden Gate Bridge. If you were at Cisco Live this year, you might have gotten to see it up close. This is the marketing icon for a bridge up here, by the way. A bridge, at its very basic level, is designed to connect one collision domain to another, one Ethernet segment to another. This was really handy back in the day when you had the Ethernet segment was literally a wire with terminators on the end of it. A bridge was designed to connect one segment to another. It was created by Digital Equipment Corporation. We'll get into a little bit more of that later on when we talk about spanning tree, because bridges were where spanning tree was created, and you can actually see that and in the descriptor units for spanning tree. But anyway, bridges were fundamentally important to networking because now allowed us to take a group of computers over here and a group of computers over there and get the two of them talking to each other without increasing the collision domain. And that was great because now we can start building networks out of these computers as opposed to just having these little islands of connectivity. Bridges are fundamentally dumb, though, because they only connect one Ethernet segment to another Ethernet segment. So while they're important in the history of networking, you hardly ever see a bridge anymore. Fun fact, though, you will see a bridge if you walk into a building and you look up and see a wireless access point on the ceiling. A wireless access point is a bridge. It bridges one network, a wireless network, to another network, a wired network, and translates packets across the two of them. If you go into an older Cisco autonomous AP, the interface that contains the IP address is actually a bridging interface. So that's a little fun trivia fact that we still see bridges even though they're kind of outdated. Well, why are they outdated? Because we have these wonderful things called switches. And a switch is basically a multi-port bridge. And if you look at this picture, which by the way is a Cisco Meraki switch, every one of those little ports that you see here is a collision domain. It's a one-port bridge. So here's what happens. If I plug a computer into port 1 of this switch, the switch is going to learn the MAC address of the device connected off of that port, and it's going to load it into a table called a CAM table, Content Addressable Memory. It's easy to remember because a CAM table contains MAC addresses, and CAM is MAC backwards. The switch learns all of the hosts that are connected off of that switch port, and it should just be one, because we don't want to have any hubs or anything hiding behind that switch port. And that's a beautiful thing, because now what you've created is a single collision domain for every device. So I no longer have to worry about having too many devices talking at one time. When a computer on port 1 wants to talk to a computer anywhere else connected to this device, it sends a frame into the switch. And the switch, reads the destination MAC address for that frame, looks it up in the table to find the port that host is located off of, forwards the frame to that port, and shoots it out the other end. And now you have reliable connectivity between the two hosts without worrying about collisions. What happens if the switch receives a frame that it doesn't have a list for? Well, it's a new host, or I'm talking to somebody that I don't recognize. That frame is addressed to the all nodes MAC address, which is all Fs, and it's flooded out of every port in the switch. And that's by design. We want to find who we're supposed to be talking to. And because we're talking about one whole domain that contains switches, or that contains devices, whoever that is bound for will answer, because by design, every member of we're now talking about broadcast domain, every member of that layer 2 network has to hear that packet and will respond with, "Hey, that's me." If not, the host should assume that the sending host should assume that who it wants to talk to is not located on that network segment, and it needs to do something else with the packet. It needs to forward it on for different handling. I mention this because we run into situations where switches start forwarding lots of unknown unicast frames, and that starts causing problems with your network design. So large numbers of unknown unicast frames cause significant issues, and there's a reason for that. At layer 2, there is no way to stop a packet. There's no way to kill it after a certain timeout value, and it will literally forward itself through the network for an infinite number of years until the power is pulled on a switch, or something else externally causes it to die.
Hey, so Tom, there
Yes.
was a question, and the question is, what if the MAC lives on another switch that's connected to the source switch? Does it get flooded out again?
No, actually it doesn't. Remember that we're talking about one giant layer 2 network, one domain where all of the hosts that are listening occur. So let's assume for the moment that we send a packet off of the switch that's here, but the switch packet actually lives down here off of the Cisco marketing icon bridge. What's going to happen is that the switch is going to have an entry in its CAM table that says that the host that it wants to talk to down here is actually located off of, say, this port right here that's connecting the two switches. So it forwards that information through this port, which is received on the connection port down here, and this switch knows that that host lives off here somewhere. So you can have a CAM table entry that says that there are maybe 100 hosts that live off of this port, and the switch here knows about them because they're all participating in the same Ethernet segment. So you don't have to worry about getting flooded across all of your ports. It's only when they don't know where that port is located, which is usually the first frame.
Gotcha. Thank you.
And just got a question on Twitter. Do Meraki switches run Cisco iOS or something else? They actually run a proprietary OS that's not iOS-like. It's something a little different. It's been a couple of years since I've looked at Meraki, and I didn't actually look at their switches, but I'll tell you that all the configuration on Meraki devices, whether it be a switch, a firewall, or an access point, is done through a Meraki Cloud Manager, so you don't actually see a CLI on those devices. The differences between Meraki switching and Cisco iOS switching and even NXOS switching are legion, and probably outside of the the scope of this webinar, but I definitely would like to follow up with you after this is over with about that. So the switch is the basic unit of layer 2. When you talk about layer 2, you should think of a switch because you're going to spend a lot of time working on them in networking. I mean, it's called the CCNA routing and switching for a reason. But what happens when a packet needs to go somewhere outside of the Ethernet domain? Well, that's where layer 3 comes into play, the network layer. So this is what happens whenever you have hosts that are too numerous for a specific domain. Remember that I told you that Ethernet likes to send packets to every node connected to it? We again reach a limitation where not every node in the network can respond to those packets. And so what we get is an artificial limitation for what's called a broadcast domain. So just like any other cocktail party that you've been to, 2 people having a conversation is relatively quiet. 200 people trying to have a conversation, even as quietly as they can, is still very loud. And so we have to segregate the amount of broadcast traffic that happens in a network. That's where layer 3 comes into play. So we change the addressing format again. We use the IP address of a device, which is different than the MAC address. By the way, this is where packets come into play. Anytime you refer to a network packet, that's the unit of work that occurs at layer 3. A packet is divided into a frame at layer 2, which is then divided into bits at layer 1, shot across a wire, and on the other end, the bits are reassembled into frames, which are then collected into packets and sent to a device. So the network layer it's not as complicated as the MAC address layer because it's a little obfuscated from that. But this is where routers live. And this is the infamous Cisco hockey puck. You will see this a lot when you start taking Cisco tests. This is the router for them. So what happens when a device needs to talk to another Ethernet segment that's not directly connected, that it knows is not one of the hosts located here? It has to go find a router to talk between those 2 segments to say these are 2 completely separate Ethernet domains, and I need to send a packet from over here to over there. And what happens is the router intercepts that packet and knows that it's supposed to be talking to a network somewhere else. It changes the MAC address of the source to the MAC address of the network card pointing at that network, and then it sends the packet on to the right destination. Then when the destination wants to talk back to the other host, it sends a packet back the other way. The router grabs that packet because it's addressed to the router's networking card and knows in the state table on the router that's actually supposed to go to this host over here. And so it facilitates the communications. It's like a big bridge, but it's more intelligent because we can do lots of other things with it. Routers are very important to the function of the internet because they connect different networking segments. But one of the funny things about IP is it's pretty useless on its own because IP can send you a packet and you'll never know it. And you never have to tell it that you got that packet. That's where we have to have some kind of functionality that ensures reliable delivery, and that's where layer 4 comes into play. Layer 4 is always nebulous because there are no devices that live at layer 4. It's actually a whole bunch of protocols. Layer 4 is the packets or the unit of work is a segment. Now that's only if you're talking about TCP traffic. If you're talking about anything else, they call them datagrams. But we're going to talk about TCP because anybody will tell you, unless you're talking about an IP address, IP is never referred to by itself. It's always TCP/IP because the transmission control protocol is required for reliable delivery of internet protocol packets. This is where your port numbers are going to come into play. So if you're thinking about, SMTP living at port 25, World Wide Web traffic living at port 80, that's how we know that that's a transport layer issue because it's creating a socket connection between one host and another host, and it's ensuring that the packets are getting there, for one thing, because when a packet is received by a destination, it sends an acknowledgement back the other way that said, hey, I got that packet. It also creates checksums to make sure that when the packets arrived, they arrived and weren't mangled. They also make sure they arrived in order because we all know that getting out of order packets is really important, really detrimental to your network. And what will actually happen is if it gets an out-of-order packet, we'll pause the flow until the right packet shows up if you're using multi-paths, and then it will reassemble them on the other end. TCP is very, very important for the function of the modern internet. Let's talk a little bit about TCP. So like I said, it's reliable. It makes sure that packets get from one destination to the other and they don't blow up along the way. They checksum each other. It's a little heavyweight because it has to checksum everything, because it has to establish the protocols. The one thing you will always hear about TCP is that it is a three-way handshake. And they will tell you this is what happens whenever any host wants to talk to another host. The first host sends a synchronization packet called the send packet. The other host sends a synchronization acknowledgement packet back the other way and says, yes, I'm listening to you. The sending host then sends an acknowledgement that it got this synchronization acknowledgement packet, the ACK, so now they can start talking. Send, ACK, ACK. It always happens in that order. What happens when you don't send them in that order, or you do something silly like you only send a send and never respond to the SYN-ACK, is you've created a denial of service attack. So if you've ever heard of a SYN flood in security, that's exactly what this is. A host sending a SYN and never responding to the ACK. The host that is sent the SYN-ACK packet, the destination, will keep that connection open for a certain period of time, waiting for the acknowledgement. TCP's three-way handshake is important. You will see it over and over again. And you have to understand why TCP is important for the purposes of the lab exam. Well, are there other protocols at layer 4 that are important? Yeah, there are a bunch of them, but the most important one is UDP. Now, I would tell you a UDP joke here, but I wouldn't be sure if you get it. By the way, that's the oldest UDP joke on the internet. UDP is connectionless, so it's weird. Wait, we have a connection protocol at layer 4, but UDP is connectionless? Exactly. There's a reason for that, because there are certain things that you want to send, but you don't care if they arrive out of order. Think about a telephone call when we packetize telephone calls to use digital transmission. If I lose a frame in the middle of that transmission, I don't necessarily care, because, you know, think about a dropped call. I can usually figure out who's talking and what word got missed in the middle of a conversation. But if those packets start arriving out of order, or the flow needs to be paused in order to pick them up, that's a big problem, because the latency in that connection could be bad. So one of the things that UDP allows for is it allows for connectionless, almost like a fire hose, or as I have here on the slide, like a broadcast, like a person with a megaphone. I'm talking, but I don't necessarily care if you listen. I just want to know that I'm talking. The smaller headers in UDP allow for great things like voice and video to be sent quickly, because I don't have to worry about checksumming the packet. I don't have to worry about all of the protocols that get thrown in there. And so they're much, much faster and much more easy to send in streams. Now, when you talk about UDP, you're going to refer to the packet unit as a datagram, because datagrams can be sent and delivered, and we don't care. But a stream from TCP has a start point, has an end point, and all the packets in the middle have to get there when they get there. And that's really important. So you're going to be tested more on TCP on the exam than you are on UDP, but know that UDP exists, because a lot of other things use UDP, like fiber channel, for instance, which we'll get into next week a little bit for the purposes of the exam. All right. Layer 5 through 7. You don't need to know anything about this for the exam. In fact, you probably don't need to know anything about it in real life. That is more concerned about the sessions that TCP creates and the way that the data that is packaged up is presented to the user. I can honestly say in the entire time that I've been doing networking, from CCNA to CCIE, I have never been asked a question about layer 5 through 7 that wasn't, which one is this? Which layer are we talking about? There are protocols that live at layer 5. SIP, for instance, Session Initiation Protocol, Invoice, and a whole bunch of protocols that live at layer 7. That's pretty much everything you deal with, HTTP, SMTP, SNMP. You don't need to know how they work. You just need to know how they're going to interact with the network. Consider that encapsulation something that you don't really need to worry about. So now that I've taught you all about the 7-layer OSI model, I'm going to bake your noodle, because guess what? Remember how I said that OSI 7-layer model is just a model? Well, we have other models that we use to describe communications in the real world. And the one that was created by the Department of Defense for the ARPANET is called the TCP/IP 4-layer Internet model. You will need to know about this for the exam. Here's what you need to know about it. The application layer in the TCP/IP model is the top 3 layers that I told you don't need to know anything about. The transport layer is the same. The network layer is called the Internet layer because this is the Internet model. And then the data link and the physical layers are combined into one layer called the network layer. Know which of these 7 layers correspond to which of those 4 layers on the TCP/IP model, and you will have no problems. Because you know what? Nobody really refers to the TCP/IP model. Most people use the OSI model when they reference things. And it's really funny because the layers we don't care about are mapped into one layer we don't care about on the TCP model, and we just change the names on a couple of the other ones. So that networking people are weird. I'll be the first person to tell you that.
Hey, Tom.
Yes.
Okay, got a long one here.
Go for it.
So this person kind of posted up here. I've seen conflicting information on layer 7 and layer 6 regarding application inspection. For example, viewing and blocking an HTTP post request. My understanding has always been that the application issues a command to the HTTP protocol at layer 7, then the SSL connection is handled at layer 6. That's why we look at layer 7 proxies when we want the application visibility and controls like blocking and post commands. That's one reason. Hold on. That's one reason to be familiar with layer 7 application proxies. Does that make sense?
Yeah, it does. It's a security-related question. So when we analyze packets in a network, analyzing the bits is useless because it's a 1 and a 0. It's electrical signals. Analyzing the frames at layer 2 isn't really necessarily important either. It's only when we get to the network and transport layer that we start really deciding what's important. IP addresses, protocol port numbers. So I'm going to block all port 443 inbound traffic to my network, which means I don't want any SSL coming in. But once we start rising up in the stack, we start diving deeper into the contents. So yes, a 7-layer proxy will look at all the layers of the OSI model, and it will allow you to get into the application layer to see things like post requests and GET requests and blocking certain pieces of it. I would argue that for the purposes of the CCNA that knowing those layers is less important, and it only becomes an issue when you're looking at the implications of what's being processed in those layers. Because remember, as you go down the stack here, as you move down the stack, everything gets wrapped up and sliced apart. So the payload from these 3 layers is just a part of this packet. Part of this segment, part of this packet, part of that frame. So we lose visibility as we go down the stack. You're right. When we're doing protocol inspection, we need to do it as close to the application as possible. But for the purposes of transmitting that packet through a device, once it gets down here, I don't care about that. I can do a choice, or I can do a conditional statement here on a port number, or on an IP address, or heaven forbid I have to get all the way down to doing it on the MAC address, which has come up before in some of my studies. But the idea is that we want to make sure that the visibility for those kinds of things occurs higher up in the model. We just don't necessarily need to understand how those parts of the model work.
Great. And there's another one that came in. I'm pretty sure I know the answer to this. But are things like OSPF, EIRGP, and ISIS layer 2 or layer 3, I believe those are layer 3 routing protocols, correct?
Yes. OSPF and EIGRP live at layer 3. ISIS is a different animal. It actually lives at layer 2. I won't cover ISIS here. The reason why is ISIS is the original routing protocol created by DEC for a lot of their applications, and it was actually not designed to run IP at first. It can run connectionless networking protocols, which live at layer 2. Things like MPLS, which you may see if you go down the service provider road, or if you work in a really advanced data center, it actually sits between these 2 layers here, network and data link. We call it a layer 2.5 protocol, layer 2.5, because it has some some aspects of data link connectivity between the links, but it also carries information about IP. So some of the newer protocols are kind of hard to shove into this model, which again is why I'm just saying, remember, this is just a model. It's a guide. It's not a hard and fast rule.
Gotcha. Wow, and then here they're coming.
Okay.
Does Fabric Path use ISIS?
Technically, yes, it does. Fabric Path is a Cisco implementation of a successor to the spanning tree protocol called Trill.
Yep.
And we'll cover that just a little bit when we talk about Radia Perlman and her work on spanning tree.
Okay.
Fabric Path at Layer 2 uses ISIS as a Layer 2 routing protocol to create multiple paths between hosts in a network. It does away with spanning tree. And believe me, I can go significantly deeper into it than you want to hear on the broadcast tonight. But yes, you are technically correct on that question.
Okay, well there you go, Graham. You are technically correct there.
It is the best kind of correct. All right.
Yes, it is.
I've had enough of models, and I don't know about you guys. Let's talk about some really interesting stuff. Let's talk about network topologies. This is really historical knowledge, and you know why? It's because almost every device out there on the planet right now runs TCP/IP over Ethernet. But you know what? For the purposes of networking theory, you're going to need to know kind of how these work. One thing that I will not talk about right now that you will need to know when you get into a real data center is something called a spine and leaf topology. It's also called a Closs fabric. By the way, fun fact, the Closs fabric for networking was created in 1952. So it's almost as old as my mother. It was written by a guy whose last name was Closs. And he talked about doing network connectivity between nodes in a spine topology. Like I said, you don't need to know this for the CCNA because it's kind of advanced. But if you get into a real data center, especially the ones that have significantly faster links, like 40 gig uplinks, you're going to see Closs fabrics deployed in great detail. But we may talk about those later.
Yeah, those seem to be becoming more and more popular, the spine and leaf type topologies within data centers and things of that sort nowadays, right?
Yes, and it's because in Cisco's historical model, which had a core layer, a distribution layer, and an access layer, most of your traffic was assumed to be going up through the core and coming back down the other side, usually into like an internet block or a data center block or something like that. But in a data center, most of the traffic that you see doesn't go up into the core and come back down. It actually goes between two devices in the data center. So what you get is, in data center parlance, anything that goes out of the data center is considered north and south traffic because it's going toward the top of the diagram. Anything that goes between servers on a data center is considered east and west traffic because it's going left and right on a diagram. East-west traffic benefits highly from spine and leaf topologies because it shortens the amount of segments that a packet has to cross before it arrives at the destination. That's why we don't necessarily care about Cisco's historical three-layer model there. And so a lot of other people like Arista and Avaya and other networking companies are really jumping on the spine and leaf topology.
Yep. Thanks.
No problem. All right, so the very first Ethernet network that you'll talk about is the bus. And this is what a bus looks like. It looks like this because back in the day when we used those big, thick coax cables to connect computers, you had to go in with a tool called a vampire tap. You had to poke a hole in that coax cable. You had to thread another cable into it with a little connector, and that's how you got somebody on the network. Literally, it involved physical labor. Buses are great because they are what Ethernet does well. These two ends of the tunnel are terminated, and the packets go down the bus, and every device that's connected to that segment listens. And like I said, if you're the host that's supposed to be talking, you hear the packet and respond. If you're not, you discard it, which is one of the reasons why Ethernet's so chatty. But bus topologies have an inherent limitation, and it's called the 5-4-3 rule. So on any given Ethernet segment, there can only be 5 segments total, of which 4 of them can be connected by 4 repeaters, and only 3 of those segments can actually have traffic on them. This is one of the reasons why we've gotten away from bus topologies, because they're not very scalable, but you may still run into them from time to time. Again, a lot of historical information. But Ethernet wasn't the only thing that was fighting a war for mind share back in the day. So this is a ring topology. And if you've ever worked with IBM equipment from about the year 2000 backwards, you probably have seen a token ring adapter. And the idea of a token ring is that every device in the network is all connected. So it has an input and an output. And you can talk to any host on this ring, provided you have an access method, which in 802.5 token ring is a physical, well, it's not a physical token, but it's a data packet that is like raising your hand to speak a question. The rings were a whole lot easier to put together and they could have more hosts, but you did have a problem. So if the token was here and the session that needed to talk was here, the token had to make itself all the way around the network before the station could talk. And so it introduced microseconds of delay. IBM played around with some things where they actually had two tokens counter-rotating in the ring so that the amount of time that a station had to wait to talk was cut in half. They used bigger packet sizes in order to fake it out, so while you were waiting longer, you sent more data in every segment. I know a lot about token ring because I actually had to work in a production token ring network when I was in college, and then I had to go to therapy and forget all of it. Another ring that you may see is a FDDI ring, a fiber distributed data interface ring. Those are big fiber rings that were used for a long time. That was the original implementation of fiber. I'm not going really into depth about a ring other than to show you what it looks like because nobody uses that anymore either. Why? Because we use switched Ethernet now. And switched Ethernet is all a star. And what you get is you get a central concentrator device, in this case a switch, and you have all of your hosts plugged into that concentrator device, from here, from here, from here, from here. And this is the building block of modern LAN connectivity. Why? Because you have one device that can talk to all of the other devices in your network. And the packets only have two hops, one to here and one out. Now, this should look very familiar to anybody who's worked in a campus LAN. You have a whole bunch of stations plugged into one device. Well, what happens if I have more than one building? Well, that's where you get the extended star topology. For reference, though, Cisco is the only people I know that actually refer to this as an extended star, but it may show up on the test, so you still need to know it. These are the stars that we were just looking at back here. This star becomes this section on the next diagram. These devices plug into another concentrator. If you have worked in a modern network, this should look extremely familiar because this is how almost all networks are built today. Switched connections plugged into other switched connections that end up talking to hosts. Those are the network topologies you need to know. They're very basic. Bus, star, ring. And the fact that you don't really even use two of them anymore should tell you how basic they are. You might get a question or two over network topologies. If you're going to take something like the Network Plus exam, you may get another 2 or 3 questions over network topologies. But I wouldn't go so far as to spend hours upon hours studying this. Just know what they look like and you should be okay. All right, enough diagrams. I've had enough of that. Let's talk about something else. Let's talk about a VLAN. Okay, vBrownbag is targeted towards server administrators, some networking professionals. Everybody has heard the term VLAN. It's a virtual local area network. What does that mean? That means I can take a switch, which is a segmented collision domain, but still one broadcast domain. So if I send a packet to a switch, it has to flood that out of every port on that switch to find an unknown unicast host. That could be a problem if you have a switch that has, I don't know, 700 ports. It's better for me resource-wise to see if I can carve those pieces up, and that's what a VLAN does. So it allows me to create an artificial segmentation of a broadcast domain on a device that can't do that, a switch. So what we do is we take a port on a switch and we say that you belong to a specific VLAN, and the port next to you can belong to a completely different VLAN. When I do that, the two hosts that are connected to those two ports are effectively isolated. They can't talk to each other anymore. That's a good thing because that means that if a packet comes in the first port and it's an unknown unicast frame and needs to be flooded, the second guy doesn't have to hear that flood. And so it preserves some of the resources. Now, one of the keys that you have to understand, though, is because we're doing broadcast domain segmentation with VLANs, those two hosts will not be able to talk to each other unless there is a router somewhere in the network that is bridging those two VLANs. Now, thankfully, one of the things that you can get now is the ability to do that routing on a switch. You'll hear that term referred to sometimes as a layer 3 switch, which is kind of silly because switches live at layer 2. What it means is that there's a software image on the switch that's capable of doing routing, and it allows you to talk between multiple VLANs. And when you consider that you can have up to 4,000 VLANs in a network, doing routing as close to the source as possible, it kind of helps your network resource contention, especially if you have one router that's doing a lot of heavy lifting. Let's talk about multiple VLANs for just a second. So every port on a switch has to have a certain designation. It's either an access port, which is a port that carries traffic for a single VLAN to an end host. That's what the majority of ports on a switch are going to end up being. Or it's a trunk port. And a trunk port carries traffic for multiple VLANs. If you guys are ESX administrators, odds are good that the networking team handed you a trunked port to your server so that you can tag multiple VLAN traffic so that you can have different networks running into your server. Now, what does that mean? Question?
Yeah, Tom, we did have one come through. Somebody asked, is there a list of known VLAN exploits and things of that sort?
Yeah, there are. There are a few out there that you have to be concerned about. A lot of them actually are what happened when you hand a naked trunk port to somebody. And I'll actually cover one of them in the next slide about VLAN 1, which is a special case VLAN. But there are ways to insert tag packets on your host and break out of the VLAN that you're in. There are ways to get around certain things. One of the ways we prevent that, though, is we don't let users tag their own packets. And I'll explain that in this slide in just a second, why that's something that you don't have to worry about in a network when you have an access port.
The big concern here, it looks like, is, there's concern around being able to send secure and non-secure packets across that same wire using VLANs.
You could. So here's why that's not really a concern. Let's say you have an access port that is configured for traffic in one VLAN. The way that we designate a packet as a trunk port is it actually can handle a little extra. So you see, right, this is a normal Ethernet packet right here, and I'm not going to go into all the garbage in the header. Where the difference happens is right here between the source MAC and the ether type. A tagged packet using 802.1q, we stick a 4-byte header into that packet, and that header, among other things, contains a little bit of information here about the VLAN that the packet is destined for. Why is that not a problem in an access port? Remember that it's interposing a 4-byte header into the frame? Well, that frame, Ethernet looks for a very specific frame size coming out of a host. It looks for a frame that is 1,518 bytes long. If you send it a frame that's 1,522 bytes long, which is what this one is, the switch will actually drop that packet, or I'm sorry, it'll drop that frame, because it considers the frame to be a baby giant. That's the technical term that Cisco uses, meaning it's a bad frame. It got information it wasn't expecting, and Ethernet doesn't like information it wasn't expecting. Now, what happens if you get a hold of a trunk port? Like if I hand a trunk port to one of my users and he figures out that he has a trunk port, yes, there is a consideration that he could tag traffic from his host, because Windows allows you to create an 802.1q header on your packets, and you could conceivably forward traffic across on a VLAN that you're not supposed to be forwarding it on, like a back channel, for instance. But inside of trunk ports, one of the things we can do is we can limit the number of VLANs that are present on a given trunk. And a smart network administrator will only hand you the VLANs that you're supposed to have. He will prune every other VLAN that's not supposed to be there. So, for instance, let's say, I'm going to throw an example here. The finance server lives on VLAN 20, and all of your users live on VLAN 30. And the only people who are allowed to talk to the finance server are people who live on VLAN 20. If you deny or if you prune VLAN 20 from the user-facing trunk ports in VLAN 30, try as they might, they're not going to get a packet on there, because as soon as that packet is tagged with VLAN 30 on a trunk link, it's discarded because it's not a valid packet for that link. Kind of makes sense a little bit, I hope.
Yeah, it does make sense. There was a follow-up question that says, aren't most VoIP port or trunk ports so that there's voice and PC on the same port?
That's a qualified yes. I actually wrote a blog post about this last year. So in Cisco land, you can create a special trunk port between a phone and a switch that allows a PC plugged into the phone to have to send traffic in the clear. So what happens is the phone, and here's how it works. The phone actually has to be running something called Cisco Discovery Protocol, CDP. The phone announces that it's a phone. The switch knows that it's a phone because it recognizes the CDP packet from the phone, and it sets up a very special trunk link. It's actually not configured as a trunk on the switch. It's you put the switch port into something called switch port voice VLAN, and then you give it the voice VLAN, which for me a lot of times was voice VLAN 10. And that means that it's expecting the phone to talk on VLAN 10, and it's expecting the PC that's connected to talk on the access VLAN, whatever that happens to be configured for on the switch, which by default is 1. If it gets a packet on any other VLAN besides 1 or 10, it discards it. And the phone actually will take all of the incoming packets from the PC and it will mark them down. So if you send it with a tag, it'll strip the tag. If you send it with a QoS header, which by the way can only be interposed on an 802.1q header, it'll strip that off too. So the phone's actually smart enough to try to avoid that. And you can configure it so that it'll pass that along, but by default it will not accept a tagged packet from the phone port. And that's a security implication, because I can walk into your network and plug into a phone port and have access if it don't.
It keeps coming here. Is it best practice to keep trunk native VLANs different than native VLAN 1, which is where
Yes.
CDP... Okay.
Yeah, it's actually in my next slide. I was going to talk a little bit about VLAN 1. For those of you who might be listening along, on an 802.1q trunk link, there's actually one VLAN that doesn't have a tag on it. It's called the native VLAN, and it's a fail-safe methodology so that if a packet or a frame is sent on that link without any kind of header, it gets forced into the native VLAN. And you have to know native VLANs for the test, because that's the difference between 802.1q and Cisco's old trunking methodology, which, by the way, you will not be tested on ever again. Cisco's inter-switch link ISL trunking no longer exists. But let's talk a little bit about VLAN 1, for instance, for example, because the question came up. So VLAN 1 is special. It can never be deleted off your switch. You can't even remove it with dynamite. And it just so happens that it's the default VLAN that carries all of your management traffic, VTP, CDP, and a bunch of other things. Best practice for your network is to get everything you can off of VLAN 1, because everybody knows that it's there and everybody knows you can't get rid of it. And by default, it's not tagged. So here's the best practice for you. Go through your switch and move every one of your user access ports off onto any other VLAN. There are 4,090-ish to choose from that aren't VLAN 1. There are a couple that are reserved for old technologies. But get everybody off VLAN 1. Pick 10, pick 100. Actually pick a lower number because of some idiosyncrasies with spanning trees, so pick like 2 or 3. Get them off there. Then when you go to create a trunk between two switches, pick a VLAN that you will never use in your network. I'm actually really fond of using VLAN 999 because it's an immediate warning signal to me that this is not a valid VLAN. Make the native trunk on that switch port 999, but don't create any other ports in your network in VLAN 999. So that way, in the event that someone gets really intelligent and figures out how to break out of your VLAN on that trunk, if the native VLAN between those two switches is not valid anywhere else in the network, it won't do them a whole lot of good. But yes, best practice is get everything you can off of VLAN 1, because even though you can't delete it, you can leave it a barren wasteland for everybody else that tries to get into it.
Awesome. Thank you, Tom.
No problem. So yeah, remember that VLAN 1 exists and you can't get rid of it because you will need that information later. So how do we get VLANs between switches? Well, we use something called VTP, VLAN Trunking Protocol, and I want to talk about this real quickly because you will learn to hate VTP, and not just for the purposes of the test. So first of all, it's Cisco proprietary. Nobody else runs VTP but Cisco. Second of all, with the exception of one newer version of VTP, you can't turn it off. It's always on. So here's what happens. You have switches that are in the same VTP domain. They have a domain name. And when they're in the same domain, they start interacting with each other. They start trading VTP advertisements. And there are three modes that a switch can be in for VTP. The default mode is server. This allows you to create local VLANs on the switch. So if I go into a switch and I say, VLAN 2, 3, 7 through 8, and 1000, I've created all of those VLANs on the switch. When you do that, and in a switch that's in server mode, that actually increments the VTP revision number. So it was 1, you created all those VLANs, and now it's 2. If you delete one of those VLANs, it becomes 3. If you add 75 more VLANs, it becomes 4. Every operation increments that counter, and I'll explain why that's important in just a minute. That counter then tells everybody else in the network that there's been a change. So for other servers, it's not necessarily as important because those servers you can create local VLANs. But for client VTP switches, they can't create local VLANs. You cannot type VLAN 10 on a client switch and get VLAN 10. It will actually give you an error message. But what you do is it gets that information from a server. So the server in that domain pushes its information to all of the clients. That's great, right? How do we know which one is the authoritative server? Aha, it's the one with the highest VTP revision number. So you typically go to one switch in the center of your network, like your main switch, and you make it a server. And you make everything else around it a client in the same domain, and now anything you create on the main server switch will automatically be populated to all the clients. That's a good thing, most of the time. However, what you're going to find is most people put their switches in transparent mode. Transparent mode switches do not participate in VTP, but they will pass the packets along provided you're in VTP version 2. In version 1, which is really old and nobody ever uses it anymore, it would actually discard the packets that it received. Transparent works like server, only it doesn't talk to anybody else. Why is that important? That's the last bullet on my slide. This actually happened to me about 2 years ago. If you have a switch in your lab that you've been messing around with and you've created like VLANs on it maybe like 50, 60 times, playing around and trying to get something to work, that number keeps going up and up and up. If you plug it into your network and it's in a different domain than the rest of the network, not a problem. It will only talk to other switches in the same domain. But what happens if you're doing some configuration and you notice that VTP domain mismatch occurred and you change the VTP domain name? Yeah, that configuration revision counter will immediately interpose itself on every other device in the domain and blast all of its VTP information to every other client and server device out there and overwrite their VTP databases. And sometimes you're an hour and a half away from the client site before you figure out that it happened, and you have to turn around and go fix it.
Ouch. That's all I got to say.
Yeah, you don't want that to happen. So here's what you do. Make all of your switches transparent is the easiest way to do it. Luckily, NXOS supports VTP version 3, which has another mode, off. Turn it off. Most people I know don't use VTP on purpose because of dumb things like I just described, where you blow things away you're not supposed to do. The idea is VTP was useful when you had to blast configuration information to a whole bunch of switches. It's not as important now. So I would just turn it off. And if you don't plug lab switches into your network until you've blown them away. And I'm not talking about write, erase, config. I'm talking about get rid of everything. There's actually a file you have to go in. I think it's VLAN.dat. When you blow it away, the VTP config resets itself. I'm actually running out of time here. I want to cover one more thing before we go too far, I want to talk about spanning tree because you're going to need to know it for the test. So let's talk a little bit about loops in networks. Loops in networks are very, very bad things. Do you remember how I told you that when a switch receives an unknown unicast frame, it floods it out of all the ports? Remember how I also told you that there's no mechanism at layer 2 to expire a packet, like a time to live on an IP address or something like that? Well, when a switch receives an unknown unicast frame and forwards it through the network, it'll eventually die unless there's a loop that causes the packet to come back around and get flooded back out the network again. It's an amplification problem. If anybody in this room has ever lived through a bridging loop, you probably are raising your hands and shaking your head right now because you know what it looks like. It brings your network to its knees. By the way, this link that I have included here, this YouTube video, that is a Google Tech Talk that Radia Perlman, who is the creator of Spanning Tree Protocol, it's her talking about creation of Spanning Tree Protocol. And what it was, the people at Digital Equipment came to her when they were about to create the first bridge, and they said, Radia, we need you to figure out how to prevent loops from happening. She goes, okay, why? So she wrote Spanning Tree over the course of a couple of weeks, and it's actually a very, very interesting talk. Fun story, though. She sent the bridge to the customer, and remember, a bridge connects two segments, so it has one port going one way and one port going the other. She's like, Spanning Tree is useless because no one would ever do this wrong. How could you screw up plugging in a port one way and one the other? Yeah, the customer plugged the bridge into itself the first time, so they created a bridging loop. By the way, you might hear people call it a spanning tree loop. That's incorrect. Spanning tree prevents loops. Bridging loops are what causes networks to come to their knees. Now, how does it work? It's real simple. You have a switch in the network that is considered to be the root of your spanning tree, and it can be any switch you want. Once that switch is designated as the root, all the other switches that are connected going that way have to pick the best cost path back to that switch. So in B's case, the best cost is this link. In C's case, it actually has two links to get back. It can either take this one, or it can take the roundabout way through B, because it's going to hear that A is sending updates. So what happens is C decides that this is the best path, and it blocks this link. That's why the X is there. So that means this link no longer exists in this particular spanning tree. Now D will go to C, and because this link is blocked, his best cost path is back to A. There's no redundancy in spanning tree because that would create a loop. So what happens is this link is disabled until something happens over here, and if this link goes down, this guy gets brought back up shortly. There's no multipath. There's no way for a packet to leave C going two different directions and take advantage of that bandwidth. That's one of the reasons why spanning tree is such a huge problem in data centers, because you take a 10 gig link out of a server, you enable spanning tree on it, and it cuts off, if you have two, it cuts one of them off. So it does a really good job of what it's supposed to do. The problem is the technology has marched on, and we don't really use it as much anymore, which is where technologies like Trill and Fabric Path come into play. So let's talk a little bit about spanning tree real quick. It uses something called a BPDU, which is a bridge protocol data unit. Remember how I told you that bridges keep coming into play even though we don't use them anymore? Here you go. Every 2 seconds, bridges send out BPDUs, and they say, here's my best cost path back to this device, which is the root bridge. And if anything changes in the network, it sends a TCN BPDU, a topology change notification. If you get a topology change notification BPDU, that means we have to recalculate the spanning tree. And we'll get into why that's important in just the next slide. So how do we decide who the root of the spanning tree is? Well, that's easy. Whoever has the lowest bridge ID is always the root of the spanning tree. How do we get to the bridge ID? Well, first thing we have to do is find the bridge priority. And when Scott told you that his Twitter handle was important because it had 32768 in it, that's because it's the default bridge priority for all Cisco switches, which is right smack dab in the middle of all of the multipliers. So they are all incremented in increments of 4096, and 32768 is the default. So you take the default bridge priority and you add the VLAN ID to it. So for instance, for VLAN 1, the default bridge priority is 32769, 768 plus 1. For VLAN 10, it would be 32778. That's the bridge ID. Okay, that's great. Now we know what our bridge ID is. Well, the problem is when they all ship out of the box, they all have a default bridge ID of 32.768. So who wins when everybody has the same default ID? Oh, that's easy. It's the lowest MAC address in the network. Okay, well, it's a good tiebreaker because MAC addresses are all globally unique. Bad problem is that, remember that MAC addresses are globally unique, so that means they started out with a really, really low number and kept counting up, right? The lowest MAC address switch in your network is probably not the one you want to be spanning tree root. Why? Because it's probably an old, busted, crappy Cisco 3550 that doesn't have enough RAM and is on its last legs and the fan's going out. No. Ethan Banks, host of the Packet Pushers podcast, a good friend of mine, he wrote a blog post one time that's always resonated with me, and he says, your network is not a democracy. Rig every election you can. How do you do that? You pick the spanning tree route. You pick the centrally located switch in your network that has enough RAM and power supplies that aren't going to go out, and you lower its default bridge priority, and you lower it all the way down to 4096. Why? Because when you do that, no other switch coming out of the box will ever have a higher bridge or lower bridge priority than that. In the event that they do, you can adjust that bridge priority. That means that you will know which switch in your network is the spanning tree route every time, and you want to keep it that way. Why? Because when something changes in your network, it has to recalculate the spanning tree. Remember I said that? Well, here's why that's such a bad thing. So we're going to talk about the original spanning tree protocol, 802.1d. Little d means it's not quite standardized yet, and we've moved on, so that's never actually going to change. By default, all spanning tree ports are blocking. So they are discarding all the packets that are received on that port until it gets the max age timer with no BPDUs received on that port. So we know it's not a root port, or there's not a superior BPDU being sent. By default, the max age timer is 20 seconds. So you're throwing all your packets away at a minimum for 20 seconds. The next stage, once max age is expired, is it's listening. Now here's where it's calculating the spanning tree, and that happens for 15 seconds. It's waiting to see if there's a superior BPDU received in the network, and if it doesn't hear one, it assumes that this port is the best cost path back to the switch. By the way, all ports have a priority, so the further down you go, if you have a cable plugged into port 1 and port 2 going to the same switch, port 1 wins because it has a lower port priority.
Hey, Tom.
Yes.
Had one come in. In relation to all this, so would you make your core switch the root?
You could. You actually need to be centrally located. One other quirky artifact of spanning tree, when it was created, nobody ever thought that networks would grow really big, so it has a diameter of 7, which means you can't be more than 7 hops away from a central switch. I would hesitate away from making it the core switch. I mean, you could, but core switches are usually doing a whole lot of other things. So you might want to make it maybe one of your distribution switches in the core or somewhere around there. It doesn't really matter as long as you know where it is.
Okay, that makes sense, and I'll go ahead and get this one out here as soon as we've already got a break here. This is more back in the VTP thing. But
Okay.
basically, if you set it to transparent or you turn it off, obviously, then you still have to configure those VLANs on every switch, correct?
Yes. Any switch in VTP transparent or VTP mode off, you have to manually configure your VLANs.
But obviously, you could probably just handle that through maybe exporting a config off of one, changing some stuff, IP information and stuff, and just getting there that way, right?
Yes.
Okay.
Yeah, in fact, that's the way I used to do it, is I'd switch the port into transparent mode, and then I had a script that I would copy down that would put down all the VLANs for that particular client site.
There you go. Okay.
If you're the only client, you should know which VLANs you have. And it also prevents you from creating VLANs you're not supposed to have on there.
Yep, because then you're not redoing it, and so it's all in all a good thing. Cool. Thanks, Tom.
No problem. So
you know what? Sorry, another one
That's
came
okay.
out. But multiple trees are supported on a network, correct?
Yes, and I'll get to that in just a second.
Okay.
By default, one tree exists for a given VLAN. On Cisco, it's actually they don't use 802.1d spanning tree. They actually use something called PBST, per VLAN spanning tree, because in the original days there was no such thing as multiple VLAN spanning trees. Cisco fixed that with their own proprietary thing, but we'll cover in just a couple slides the difference that they actually have a standardized version of it now. So we're listening for the network, and we're going to listen for the maximum forward delay, which by default is 15 seconds. Once we've got the forwarding delay figured out, we have the spanning tree built. But like all good engineers, we have to make sure that the stupid thing is going to work before we institute it. So in stage 3, in the learning phase, we're actually making sure that the route is stable. And if we don't hear any superior BPDUs or nobody screws anything up for another forwarding delay of 15 seconds, now we can start forwarding traffic. Hooray! That was 50 seconds. Anybody in here ever had a network go down for 50 seconds? Had your computer go offline for 50 seconds? After about 10, you're wondering what's going on with this stupid thing. By default, max age plus 2 forwarding delays is 50 seconds, and that's the minimum amount of time that it takes for a network to come up. Now, you can play with max age and forward delay, but remember that they're also impacting on other things, and you're already sending BPDUs every 2 seconds. If you try to lower that any more than you already have, your network's going to get congested. In fact, if you Wireshark a switch port while you're trying to do something, you'll see the switch sending BPDUs. That's just what it does. I've learned to filter it out. So what happens when we want to speed things up? Well, Cisco realized that spanning tree needed some fixes, the vanilla spanning tree out of 2.1D. So one of the first things they did was they created port fast, which is I'm going to force the port into forwarding mode immediately. Yay, that means the workstations that are connected on access ports don't have to wait 50 seconds to come online. That's great. Users can get online and start working. Why is that bad? Well, it's forced into forwarding mode, which means it's not going to run that spanning tree calculation. What happens if I plug a switch into that port? That could be bad. Well, that's why Cisco created something called BPDU guard. It does exactly what it says. It looks for BPDUs on the port, and if it gets a BPDU, it shuts the port off. You're not supposed to be getting BPDUs here because you should be in a workstation. Something's wrong. I'm going to disable this port, send a trap to my administrator, and say, hey, come fix this. There's also one called BPDU filter, which will remove a BPDU from the port, or it will actually transition the port into a regular spanning tree port, depending on where you configure it. Nobody really uses filter anymore. Everybody uses guard. Port fast is beautiful for in workstations, but only enable it on in nodes that are access ports. There's a port fast trunk that you can enable in Cisco. I don't recommend that. Let the trunks go through your normal spanning tree calculations. Cisco also has something called loop guard, which protects against unidirectional link failure. Basically, it means if your root port was getting BPDUs and stops getting them for some reason, it's going to put the port into disabled mode until it gets another BPDU in the event that it's actually sending traffic back the wrong way and not getting a reply. Loop guard isn't really used a whole lot, but root guard is. Root guard's enabled on all your root ports, and it enforces the root bridge placement in your network. If someone sticks a root bridge on there that isn't supposed to be there and has better priority than the one you created for some reason, root guard will put the entire network into a disabled state until you figure out what's going on. Why are those three things important in the grand scheme of things, other than the fact that most people enable port fast on access ports? Because those three things ended up getting built into the next version of spanning tree, rapid spanning tree, which is a whole lot better. In fact, most things should be using rapid spanning tree or rapid PBST by default. Why? Convergence times went down to almost nothing. It takes 6 seconds to converge a rapid spanning tree, and that's assuming that a TCN isn't received. TCNs can be processed almost on a microsecond level. Why? Because when you do a rapid spanning tree, every switch creates a backup port. So in the event that the root port goes down, the backup takes over. There are only 3 phases to a rapid spanning tree. You're either discarding, you're learning your network topology, or you're forwarding. We like talking about 802.1D because as the oldest, slowest, most well-documented version of spanning tree, it's easy to teach, but you should be running rapid on all of your devices. You should make sure it's turned on, and you should make sure that it's what's working through the network, because that way network topology changes aren't going to blow anything up. But one of the hiccups with rapid spanning tree and with 802.1D spanning tree is it doesn't really handle multiple VLANs very well. Cisco wrote a technology that would do that per VLAN spanning tree. 802.1S is multiple spanning tree. Why is that important? Well, it allows me to create a spanning tree for each VLAN or for a VLAN group. And I pulled this diagram here from a vendor other than Cisco because it represented what spanning tree was a whole lot better. So remember I told you that it blocks links that aren't best cost back to the root? Normally what that would mean is if A is the root, then this link gets blocked because this link is better, and this link gets blocked because it's not better. So you only have one path back to A, right? And that one path has to carry every VLAN. Well, that means I've got two links here that aren't being used for anything. So what I can do is I can create a multiple spanning tree instance on all of these switches. And what I can say is for any given switch path, I want to forward all of my VLAN 10 traffic over just this link. And I want to forward all of my VLAN 20 traffic over this link. And same way for VLAN 30 and 40. Now, between switch A and B, I'm going to let all the VLANs transit. Why? So that when this switch sends traffic for VLAN 20 to switch B, he can send it over to A where it's supposed to be, and vice versa. This allows me to create fault-tolerant connections that fully utilize links. Most other vendors other than Cisco are going to default to using multiple spanning tree because it just makes more sense. You may have to know about multiple spanning tree for the test, but only what it is. You probably will not have to configure it. In fact, I almost guarantee you won't have to configure it. That's spanning tree in a nutshell. You don't need to know it a lot. It's actually about half of the CCNP switching test is learning spanning tree, and I know because I had to help a guy get through it, and we spent hours upon hours whiteboarding spanning tree. But you need to know about it in data center because of what it does, because it blocks links, because it causes reconvergences, because you want to get rid of it if at all possible. If you can't get rid of it, you need to minimize it as much as possible. That's why a lot of places run IP to their top-of-rack switches, is so that the backbone of their network, their spine, is not running spanning tree. It's all layer 3 packets. Now, who has a question?
Give me a second here.
Okay.
Okay, so I've got one here that says, would you recommend PVRST or MST?
If you're running only Cisco devices, PVRST is better because it's easier to configure inside of Cisco. MST requires a little bit of work. It's not the easiest thing in the world to do. You actually have to enter an MST configuration mode. You have to split your VLANs up. It takes planning. PVRST works. It's just like every other Cisco technology. We don't really understand how it works, but it works. So if you're only running Cisco, turn it on. If you're ever going to put a Juniper, Brocade, Arista, Huawei, any other switch in your network, you're going to have to use MST.
Gotcha.
Now, I will tell you guys that we skipped a lot about IP today. We skipped routing protocols. We skipped RFC 1918 addressing. Again, there is so much content for this exam that you kind of have to be aware of, that you want to spend time on the topics. I skipped over a lot of these at a very high level because I think you need to know them, but I also think that you need to make sure you understand some of the other things. So I'm going to talk a little bit about them next week. I'm going to talk a little bit about NXOS as well, because NXOS is the version of iOS you need to know for the exam. We're also going to talk a little bit about the product knowledge that comes in on the other exam, which involves knowing the differences in the various Nexus switches, the Nexus 5K, the Nexus 2K, why you want one and not the other, and how they all work together.
Well, great. Thanks again for your time, Tom, today, and being able to hop on and share your knowledge. And we look forward to getting you on here again next week and kind of following up here. I'm not seeing any. Oh, actually, hold on. Here came in a question. Is data center bridging on this cert?
I do not believe they test over data center bridging. Again, it boils down to the CCNA is the type of exam where they want to teach you the very basics, how to get on an NXOS CLI and not blow the switch up, how an NXOS CLI works, the basic show commands, and a little bit of architecture. Now, the whole purpose of the CCNP professional level exams is to dive deep into that. So there's a test over routing and nothing but routing. There's a test over switching and nothing but switching. So if you see data center bridging, it's probably going to be in that exam group because it's a little bit more advanced topic.
Gotcha. So if anybody else has any questions, go ahead and get them posted now. I'll give you guys a couple seconds, maybe see if we can get those out the door. Um, so go ahead and post them to the question window or Twitter.
Yep, and if you want to use the hashtag vBrownbag, I will keep an eye on that. If you have any questions for me, you can also mention me on Twitter. I spend a lot of my free time there since it's kind of part of my job.
Don't we all? All right. Actually, one did come in here. Use
Okay.
port fast trunk for ESXi host trunk ports.
You could, and the reason why is because when you port fast trunk essentially causes the switch to fail into forwarding mode right away. And if you know that you're talking to a host on the other end, you can turn on port fast trunk. It's different now that you have hosts that are capable of taking trunks. So I would feel comfortable with that. But make sure that you use the description command on the interface in NXOS that says this should be pointing at this host. So in the event that that switch gets moved around or repurposed or something like that, you know to turn that command off so that you don't blow up your network.
Gotcha, makes sense. And I was pretty sure that was, I think that used to be, if anything, maybe now it's a little bit changed because the host can see it, that was kind of more of a best practice to either use port fast or turn it off on those ports for the hosts. All right, so it's looking like the questions have kind of died down at this point. Just one other thing to note again, guys, is if you do have any of those routing, the Cisco CCNA routing and switching questions, please do get them over to Scott McDermott on Twitter. That's at ScottM32768, and he's still doing that contest, so you guys have a chance to win a book there. And with that being said, I'm going to go ahead and be done here for tonight. And yet again, Tom, thanks again, and we look forward to getting the follow-up next week. Thank you, everybody, for joining us tonight.